Okay, guys. Now, we're back in chapter 2, and we've been looking at a position versus time graph and a velocity versus time graph. Okay? So, let's look at Stop and Think 2.2 on page 42. Here we've got a position as a function of time graph. The question asks us which one of these velocity versus time graphs goes with our position versus time graph. Okay? Now, let's look at it. From here to about here, we're dealing with essentially a straight line. And then it curves and we flatten out and stop changing location. Here we've got a slope to the right. So this is a positive slope. So the velocity in this section is positive. That eliminates this guy because it's starting out at time 0 with a velocity that's negative. Okay? That leaves us B and C. Now, if I look at B, velocity is changing with time and then the velocity levels out and stays constant, but it's a non-zero constant. Here, the velocity is constant and then the velocity goes to 0. It's slowing down here and then flattens out. So if we look here, velocity is constant at a positive value, and the velocity is slowing down, and then it's sitting still, velocity goes to 0. So the velocity versus time graph that goes with this position versus time graph is graph C. Okay? All right, now, let's look at non-uniform motion where velocity changes with time. We have an acceleration. Let me scroll the screen up for us so that we have something to work with. Okay? Now, we know that acceleration is a change in velocity with time. A acceleration is delta V, delta T. We know that if the acceleration vector and the velocity vector point in the same direction, something is speeding up. If the acceleration vector and the velocity vector, okay, so if there's our velocity vector, there's our acceleration vector, then we know that velocity 2 is going to be longer, greater than velocity 1. If here's velocity vector 1, and at this point the acceleration points in this direction, we know that velocity vector 2 is going to be shorter. Okay? That's some general things we know. Now, we know that average acceleration, delta V over delta T, can be over any time interval, okay? What we want to start talking about in this section is uniform acceleration. Uniform acceleration means that the acceleration is constant. So that a velocity versus time graph is a straight line okay? And the position versus time graph is a curve. All right, we're gonna walk up to the front board because this will drive me crazy having to continue to run across to advance the screen. You got your notes. We got pretty images. I'll make sure that you get a hold of them. Okay, so let's move up here to this board so I can work. All right. Now, okay, let's say that we have a graph here. Velocity versus time. And here's cars 1 velocity as a function of time. And here's car 2's velocity of a function of time. I can see that velocity for car 1 as a function of time is a straight line, okay? And the slope of that line is greater, it's steeper. That means its acceleration has to be more. The velocity of car 2, okay, as a function of time, the line is straight, but it's not as big a slope, so the acceleration here is greater. So let's say if I dot across right here, so that I want to find when they're both going to reach the same speed, I can see that car 2 reaches the same speed as car 1. You know, they both reach, let's say, 45 meters per hour at different times if they both start off from the same location. Okay? So velocity versus time graph. Now, the acceleration equals the rise over the run for a velocity versus time graph. Okay? So in other words, the acceleration is the slope of this graph. Now, let's look at figure 2.25 on page, well, I don't know what page it is in your book, but let's look at it, okay? Now, let's look at the graph here. All right. Now, if I look at this graph, well, this set of graphs, here I have uniform motion, which means that acceleration is 0 and velocity is constant. So if we look at a uniform motion, position as a function of time graph is a straight line. Velocity versus time graph is a straight line, and it's a horizontal line, and acceleration as a function of time is 0. If we look at uniform acceleration, where acceleration is not 0, then a position as a function of time graph is a curve. The velocity versus time graph is a straight line, but it's got a slope that's not 0. An acceleration of function of time is a nice straight line that is not 0. So just by looking at the graphs, we can tell uniform motion, acceleration is 0, from uniform acceleration motion where the acceleration is not 0. Okay? All right, now, let's look at equations for uniform acceleration. Now, since in uniform acceleration, we know that acceleration is constant, I can say acceleration is equal to delta V over delta T. So I can say that A delta T is equal to V final minus V initial. Or I can say that V final is equal to V initial plus A delta T. So notice, if acceleration is positive and velocity initially was positive, then the magnitude of velocity final is going to be larger than velocity initial. If the sign of these two are opposite, the magnitude of velocity final is going to be less than velocity initial. Okay? Important equation. Now, it's not the only equation that we're looking for. Okay? Now, if I look at a velocity versus time graph, and I were to look from a time t initial to a t final, and we were to think about the area under the curve. In fact, I'll start out at here, t initial to t final. So I look at the area under that curve. Yeah, I'll go with my original. You guys are in calculus, but you may or may not have talked about integration yet. Okay? If I want to know the area of this curve, I'm going to do an integration. And the area under the curve, it turns out, is equal to delta x. Or I could think about it as dx is equal to the integral from t initial to t final of v dt. The velocity is a function of position, velocity is a function of time, d time. Now, the velocity here is changing as a function of time, but we're looking at the area. Okay? Since velocity here, the acceleration is constant, I can think of dx is equal to the area. Now the area is equal to 1/2 the base times the height. So if I was to look at this part, 1/2 the base times the height will give me this area. And the area under here would be the h would be this guy. The area under here is just the delta t times that v initial. Okay? So if you put those guys together to try to get, so it would be 1/2 delta v delta t plus v initial delta t. Okay? Now if we work a little magic with this, what we get is that delta x is equal to, okay, you ready for this? V initial delta t plus 1/2 a delta t squared. Now there's some magic in there. Note, remember that delta v is v final minus v initial. Okay, so that I could say that that is equal to a delta t. So I could substitute that in for there, and that's how I get this equation. So if we want to take it one step further, I can say that x final is going to equal x initial plus v initial x delta t plus 1/2 ax delta t squared. And I know, of course, v final equals v initial plus a delta t. Okay, now there's one more equation that we can eke out of all of this. the last equation I'm just going to give you, I'm not going to worry about deriving it. It says v final x squared equals v initial x squared plus 2ax delta x. Okay? And these are equations for uniform acceleration. Remember our one equation for uniform motion. Okay, here acceleration equals a constant. Here, velocity equals a constant. And that's because acceleration is 0. And it was x final equals x initial plus v initial delta t. Okay? So there's our sets of equations. Now we're going to do some problems. We're going to look at some problems at the end of the chapter. Okay, so I hope you got your book, because we're going to use it. Okay, so if we flip to the end of chapter 2, okay guys, we're going to look at, get to the right page. We're going to look at question 17. It's on page 60. Page 60, number 17. Okay, it says a speed skater moving to the left across frictionless ice at 8 meters per second hits a wide patch of rough ice. She slows down steadily and then continues at 6 meters per second. What is her acceleration on the rough ice? So I'm going to call this my x equals 0 position, and then we're at x final. And it doesn't tell us how wide that patch is, okay? But here I know the velocity was minus 8.0 meters per second. And your book says solve everything to 3 significant figures. I'm going to give you the number of significant figures on a math problem when I have you do it, okay? It says v final here, minus 6 meters per second, because this is normally our positive direction, this is normally our negative direction. It asks us what is her and it says this is minus 500 meters. It did tell us the width of it, and asks us to find acceleration. Now let's look at the pieces of information I've got on my rough sketch. Okay, I've got my x initial, I've got my x final, I've got my v initial, I've got my v final. I want to find delta y. I want to find acceleration. Now if you look at those equations for uniform acceleration, I want an equation that's got the initial and final velocity, it's got initial and final position, and it's got acceleration. I don't know anything about time. So looking at it, v final squared equals v initial squared plus 2a delta x has to be my equation. I've got velocity final, I've got velocity initial, I've got change of position. The only thing I don't know is acceleration. So I go a minus 6 meters per second quantity squared has to equal minus 8 meters per second quantity squared plus 2 times a times a minus 5 meters minus 0, delta x, final minus initial. So let's work it out. 6 squared, that's 36. So I have 36 meters squared over second squared, 8 squared, 64 meters squared over seconds squared plus 2 times A times minus 5 meters. So 36 minus 64 divided by 2 divided by a negative 5. Acceleration here is a plus 2.8 meters per second squared. That plus is important because it tells us the acceleration vector is pointing in the opposite direction from the velocity vector. Okay? Now, let's look at problem 18, same page. Problem 18 says a Porsche challenges a Honda to a 4-meter race. Because the Porsche accelerates at 3.5 meters per second squared, is larger than the Honda's 3.0 meters per second squared, the Honda gets a 1-second head start. Who wins and by how many seconds? So here's our starting line, x equals 0. And they're coming out here to x equals 400 meters. Okay? So, I've got the Honda and I've got the Porsche. The Honda starts here at x equals 0. For the Honda, it's at t equals 0. And he's going to get here at t final, and his acceleration is 3 meters per second. For the Porsche, he's here at t equals 1 second. He's here at, I'll call it t final Porsche, okay? And his acceleration over this period is 3.50 meters per second. So I want to calculate t final for the Honda and t final for the Porsche, okay? So I've got two calculations. For the Honda, then I'm going to say, let's see, x final equals x initial plus v initial delta t plus 1/2 a delta t squared. X initial is 0. Velocity initial for both of these is 0. Delta t I don't know, plus 1/2 times the acceleration, 3 meters per second, delta t squared. Well, anything times 0 is 0. So I get 400 meters is equal to 1/2 times 3 meters per second squared, delta t squared. So 400 divided by 1.5 says that delta t squared is 267 seconds. So I take the square root and I get delta t